Hello, physics fans. So let's look at moment of a force. While looking at moment of a force, or we'll begin with our definition. So we're going to define moment as the force times the perpendicular distance that is between the force and the line of action. So we'll be using certain terms of pivot or fulcrum. So let's begin by looking at an example. Our first question is asking us to calculate the moment of a force. A force is a vector. We'll be using arrows to show the direction to which this force will be going. So we're looking at a force of 10 newtons and it's acting at a distance or a perpendicular distance of 4 meters away from our fulcrum. Now, using the equation, and our SI unit would have been our Newton meter, would actually end up with moment is equal to force times perpendicular distance. Therefore, we'll end up with 40 Newton meter. And we need to also indicate the direction this force will actually be going or cause this object to spin. Now, this upward force will cause this plank to spin in a clockwise direction. I want you guys to picture the hand of a clock going around. Now, the direction the hand of a clock goes around is called clockwise, while the opposite direction will be called anti-clockwise. Or question 2 would focus on finding the moment of the force, but essentially, what I want to bring across, we have the same force, but we're acting closer to our pivot or our fulcrum or our turning point. You can imagine holding onto a door. So the door would be the point you're applying the force, that point you hold onto the door. And the hinge would have been your pivot or your fulcrum. The closer you are to that hinge of a door is the less turn effort you'll actually see. And you look at this mathematically with this equation or this solution. Notice that we're having the same force, but we're closer to our hinge. Therefore, we'll actually end up with 20 Newton meters. Now let's look at our principle of moment. Now the principle of moment states that when a body is in equilibrium, so equilibrium is a state of rest or a state of being. Right now, if you're seated on a chair, you're in a state of equilibrium vertically. So you're pushing down on that chair, and the chair is also pushing down, pushing back up on you. So vertically, you're not moving. Therefore, you're a state of equilibrium vertically. So let's look at this now. When our body is in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anti-clockwise moments about the same point. So below the question 3, we'll be looking at a seesaw scenario. I'm sure we all actually sat on a seesaw and would experience that state of equilibrium. We're expected to find a distance here. And when you're looking at moment, one important thing to do is to consider each force individually as you go along. So we're gonna consider our 4 Newton force and see if it will cause this seesaw to spin clockwise or anti-clockwise. So we're gonna look at our solution here. So we're gonna use the principle of moment, which says that the sum of, so that fun looking symbol there means sum of the clockwise moment is equal to the sum of the anti-clockwise moment. I'm using subscripts, so FC would be my clockwise moment, DC would be my distance or anti-clockwise moment, FA would have been the force for anti-clockwise moment, and DA would be the distance for anti-clockwise moment. So pause the video, ask yourself, would the 4 Newton cause that plank to spin clockwise or anti-clockwise? Or would it be the 6 Newton? That's an important thing to note. So now first we're going to try to find our clockwise. Pause the video, figure it out, and then we're going to come back. Now we're back. Now actually, is a 6 Newton force would actually cause our plank to spin down, go down, and I want to rotate in that direction. Therefore, that will bend clockwise. So that will be 6 Newton times dc, or distance is going to be d, is equal to the anti-clockwise, which would have been 4 Newton times the distance of 2. Both distances are taken from the same point. That's really important. When we do our calculations, we end up with a distance of 1.33 meters. So these two forces, a 4 Newton force at 2 meters, will be in equilibrium with a 6 Newton force at 1.33 meters. Okay, let's look on another question. What you could do right now is to pause the video and see if you're able to answer this question. Same, calculate the weight of a plank so that it balances on the pivot. Good. Now notice there's a CG that is placed right above there. Later on, we're going to talk about what this means. This means center of gravity. And we believe that this is a point where the entire weight of an object acts. So we're going to do an activity at that point in time when we're talking about that. Now, pause that video and see. Now, what I want you to think, which one of the forces will actually cause our plank to spin clockwise or anti-clockwise? Would have been our 10 newtons or our unknown force. Now, you could use this example at the top. Notice that the force that is going down on the right hand side was the one that caused it to spin clockwise, and the forces that is going down on the left hand side cause it to spin anti-clockwise. Clearly, the questions are quite similar. Therefore, we'll know that the 10 Newton force will be that one that is caused it to spin clockwise. Time at distance of 2 meters is equal to Fa, the anti-clockwise force, times a distance of 3 meters. Again, all two distances are taken from the same point. You'll end up with a force of 6.67 newtons where that is concerned. So now that would have caused our plank to be in equilibrium. Now there are two conditions for equilibrium. The first is the sum of the forces in one direction equals the sum of the forces in the other direction. And I use this example initially saying that vertically you're not moving upward or downward because you're in a state of equilibrium, because the force you're applying to that chair you're sitting on, or desk or bench, or whatever you're sitting on, is equal and opposite, so you won't be moving. Or if you're gonna push against a wall, the forces will be equal and opposite, therefore the wall or you would not be moving if you're held steady. The other condition is what we're looking at so far. The sum of the clockwise movement about any point is equal to the sum of the anti-clockwise movement about the pivot, or about the same point. That is the same thing there. Now, I spoke about the center of gravity earlier, and center of gravity is defined as the point in which the entire weight of an object seems to act. So good activity, your pen or pencil, you could you could guesstimate or use your guesstimator where the center of your pencil is, or you could use a ruler. So if you have one of those rulers, it's a 30 centimeter ruler. So what you could do, find the center of that would have been 15. So it's a regular shape, therefore the center will be 15. Put it on your finger and the ruler would balance. If you put the ruler to the right above where it made the 15 mark, be above, to your right, and release the ruler would fall in the direction where the center is. So pull back the ruler back to the center, put the 15 mark to your left, the ruler would fall to the left. So that's one of the reasons why we believe that the weight acts at the center. So almost everything that we notice, your weight seems to be at the center, and you're most stable when you're centered.